How we doing? Doing all right? Ready for the weekend? Okay. Any questions about anything before we do another example here? Make sure we're all on the same page with inverse matrices, and then go on to the last topic. All right, well, let's go ahead and do this example. We skipped over it last time to do one of the matrix equation examples. I want to go back and do this one with one of the 3x3 matrices. So we've got this matrix C, and we want to find its inverse. What do we do first? Need the stool. What do we do first on this one? Good. All right, so first thing I want to do is take the matrix, augment the identity matrix. And then use our Gauss-Jordan elimination to rewrite this matrix with the identity on this side and then the inverses on the other side. So first step, what do we need to do now? What's the first step in elimination? Get a 1, right? Now, in this one, to get a 1, if I use this row, I'm going to have to divide everything by 6, right? Might be a little bit nicer to divide this one by 2 instead, just because I won't have as many fractions, perhaps. So let's flip-flop row 1 and row 3 first. Just try to minimize. I mean, I'm still going to get a fraction anyway, but at least minimize the fractions that I do have. Oops. Said flip-flop the rows. Make sure you flip both rows, unlike what I did the first time there. So moving the third row up to the first row, flip-flopping those, do the -2, 0, 4, and then don't forget to flip this side too, which is what I had forgotten to start with. Make sure you flip your 0, 0, 1 up to the top as well, and the 1, 0, 0 all the way to the bottom. Main reason why I'm doing it this way is to just make sure that if you need to flip rows to get a 1 up there first, make sure you flip everything, not just the left-hand side. Make sure everything gets flipped. All right, so to get a 1 in the upper left-hand corner here, what do we need to do? Yeah, -1/2, good. -1/2, row 1, replace row 1. So when we do that, we get 1, 0, -2, 0, 0, -1/2. Again, don't forget to do everything all the way across. It's easy to forget things. It's easy to make little arithmetic errors as you go. So be careful on these as you're doing them. After we get the 1, what are we going to do next? Get the zeros below it, right? So to make the -2 into a 0, what do we need to do? Yeah, multiply row 1 by 2 and add. We also need to make the 6 into a 0, so we'll multiply row 1 by -6 and add. Good, yep. So we'll do 2 row 1 plus row 2, replace row 2, and -6 row 1 plus row 3, replace row 3. Oops. So again, since we're working off of row 1, that doesn't change row 1, so I just rewrote it. We go through our arithmetic for the next one. This should definitely be a 0, so we're making it be a 0. 2 times 0 gives me 0 plus -1 is -1. 2 times -2 gives me -4 plus 1 gives me -3. I get 0, 1, and then I'll get 2 times -1/2 is -1 plus 0 is -1 here. For the third row, again, we'll get a 0 here. We'll certainly keep a 2 here. Good. -6 times -2 is +12 plus -6 gives us +6. I'll still get a 1 here and a 0 here. -6 times 1/2 is +3. And add it down, we'll get the +3. That's a 6. It's an ugly looking 6 there. Are we okay with those 2 steps that we just did? Not any different than things we've done before. It's just we have to go all the way across, right? So far, so good? Next step. You get another 1 right here where that -1 is. What do we need to do to get a 1 there? Multiply by -1. We'll do negative row 2, replace row 2. And all that does is flip your signs all the way across row 2. So the rest of the matrix should be the same, but your third row should now look like 1, 3, or sorry, 0, 1, 3, 0, -1, +1. What's the next step? Yeah, 0 below it, right? What do we need to do to get a 0 below it? Good. -2 times row 2. Added to row 3. Replace row 3. We're not doing anything to row 1. We're working off of row 2, so it doesn't change row 2 either. What do you get in row 3? Well, what's the first entry in row 3 for certain, without any doubt? 0, right? The next one, without any doubt, is also 0, right? Because we're rigging it that way. What's your third one? It's also a 0, isn't it? Because you're doing -2 times the 3, which is -6. Add to the 6, you get a 0, don't we? Right? We can fill out the rest of the row. We'll get a 1 here. We'll get a +2 here. And we'll get a 1 here. Honestly, it doesn't matter. Because at this point, what would be your next step if you're trying to do your row reduction, your elimination, I mean? I need a 1 right here. Can I get a 1 right there? No, we get a row of 0s here, don't we? So what did that tell us back when we were solving systems of equations when you got a row of 0s? There's 2 possibilities, right? We got a row of 0s. You either had no solution or infinite many, depending on what the constant looks like, right? In this case, notice that our constants over here are definitely not 0s. So we can't get the infinitely many solutions case. It doesn't work that way for inverses. We get no, if we were thinking about this from a system of equations standpoint, we have no solutions. So what this tells us right here is that C does not have an inverse. So if you go through your elimination process and get a row of zeros there at the bottom of your matrix, like that, that tells you there's no inverse. And there's different ways to say that it doesn't have an inverse. You might hear that it's not invertible, is one way to say it, or it's singular. That's a fancy way to say it. But what I'm looking for is if you go through your elimination process and you get that row of zeros there, then you get no solution. Or sorry, you get no inverse. That was why I wanted to go through this example in particular. That's okay? All right. So, pardon me. We've done these. I'll leave the other ones for practice because we talked about how to solve the matrix equations, right, with using inverses. So I'll leave those for practice. I'll get some solutions posted up on Moodle as well for you if you want to look through those. But I do want to start today, our last piece here. Last thing I want to do, everything we've done so far in this chapter has been working with solving systems of linear equations. But sometimes we need to solve systems of non-linear equations, and so that's what we're going to talk about today. And again, this is the last new thing that we're going to talk about. So we'll talk about this today, finish it up on Monday, and then you'll have your exam over chapter 9 on Wednesday. And then we'll review for the final on Friday. So that's where we're going to be heading in the next week. So let me switch over here. All right. Pardon me. So rather than going through some long-winded explanations, let's just get right into it and try to solve some of these things and figure out what we're actually meaning by solutions. So remember when we have systems of linear equations, there are exactly 3 possibilities for the number of solutions. What are those again? Good, yeah, no, one solution, no solution, infinitely many solutions, right? That's the 3 possibilities. When we go to non-linear systems, that may not hold anymore. We may get a whole bunch of different types of solutions. So just looking at this particular example, this first example, why is this not a linear system? What in the first equation in particular tells you that this is not a linear system of equations? The x is squared, right? Remember, for linear systems, when you have a variable, that variable has to appear to the first power, right? Can't be inside any other functions, can't be squared, can't be divided, right? It has to be just a single x, a single y. That's all you get, right? You multiply by numbers. All right, so that first equation in this case, this first equation is not linear because of the x squared. As a matter of fact, if I solved this for y, which I'll do here, I'm going to use that here in a minute anyway. If I solve this for y, I would subtract the x squared over, y equals 8 minus x squared. What kind of shape do you get when you graph that? We'll see that. I'll graph that already provided for you. But what kind of shape do you get when you graph that? It's a parabola, right? Notice that that parabola is facing downward versus upward because of the minus sign in front of the x squared. Thinking about it from a graph transformation standpoint, that negative is on the outside of the x squared, so it makes a reflection, a vertical reflection over the x-axis, right? That's why the U-shape up flips the U-shape down. And then the 8 is a vertical shift, so it goes up 8. And that's why we've got that parabola here that's going downward because it flipped upside down, but it goes up to 8. shift everything up 8 units. It's a good idea. I thought it was a good idea to remind you about those graph transformation things we did. All right. Notice that the other equation gives you the graph of what? What kind of a graph do you get for the other equation, the second equation? A line, which you also see on the graph, right? So what we're interested in, basically, in this particular example is where does the parabola and the line intersect? That's what we're looking for. In this case, we see there are going to be 2 solutions just from the graph, right? If we think about how we could shift this line a little bit, certainly we see lots of scenarios where we can get 2 solutions. You can probably see a scenario where you get no solutions by taking that line and go all the way off the top, right? But you could also have a scenario where you come in and then just barely touch the graph and keep going and have exactly 1 solution as well. So in this case, just for this specific case, if I just think about shifting the line around, I could see no solution, I could see 1 solution, I could see 2 solutions. I can literally see the 2 solutions here, right? Okay. So much like what we talked about when we started doing systems of equations, we can do this with a couple of different methods. We can either do substitution or do elimination. This one I'm going to choose to use substitution because I've already solved for y in that first equation. So remember, when we do substitution, we take what we have for one of the variables from the one equation and plug it into the second one, right? That's what we do. So we'll take this, plug it in for y here into the second equation. And let's just solve. So distribute the -2 through. You'll get x minus 16 plus 2x squared equals -6. We have a quadratic equation here. How do we solve quadratic equations? What do we want to do? Yeah, we're going to factor, right? Before we factor it, what letter do we have on one side? 0, right? So I need to add the 6 over. So 2x squared plus x minus 10 equals 0. I think this one factors. If you don't see how to factor it right away, what can you always use? You can always use quadratic formula, right? Every single time? Yep. Good. So, but this one I think factors. If I use a 2x and an x, that gives me a 2x squared. I think a plus 5 and a minus 2 here will work. Again, anytime you solve a quadratic equation, you should always see the factors first, because if you can factor it, it's faster. However, it's only faster if you can see how to factor it. If you don't see how to factor it right away, flip over and use quadratic formula. Quadratic formula will always work, whether it factors or not. All right, so then we set each piece equal to 0. First equation there will give you x equals 5/2. Second equation will give you x equals 2. Not quite done, almost done. We're not quite done. These give us the x coordinates of these 2 points, right? How do we find the y coordinates? Yeah, going back into that first equation where we have y equals 8 minus x squared, right? Just take your x's, plug them back up into that first equation. That'll give us our y's. So if we have x equals, oh, everything moved on me. That was weird. If we have x equals -5/2, then our y will be 8 minus -5/2 squared. This will give me 25 over 4. 8 is 32 over 4. So it looks like we get 7 over 4. No, can't be 7 over 4. Really, yeah, it is. I'm going to get the wrong point. If x is 2, then y is 8 minus 2 squared. 2 squared is 4, so I just get 4 here. So our two solutions then as ordered pairs would be -5/2 7/4 and 2, 4. What questions do you have on that? This process should look very similar to the process that we did for substitution back when we did systems of linear equation. Agreed? It's the same. Just end up with an extra solution here because we have different types of shapes that we're looking for where they cross. Let's see if we can do this next one. We've got x squared plus y squared equals 25, and y equals 2x. Well, y equals 2x is what kind of a shape? The second equation gives you what kind of a shape when you graph it. Not quite. A vertical line would be x equals a number. So this one's, but you're right, it is just a line, right? The slope is 2, yeah, good. So we got a line going that way. Do we know what the graph of x squared plus y squared equals 25 is? Well, it ends up being a circle. The circle that's centered at the origin. It has a radius of 5. So if I think about a line and a circle, how many places do you think that might intersect if you have a line and a circle? 2, right? So we're probably, assuming they actually do intersect, we're probably looking for 2 solutions here. Again, much like the parabola case, I might have the line not intersect the circle at all. It's possible I could shift that line somewhere. It's also possible I could make the line just barely touch the circle and keep going and have 1 solution. But this goes through the origin, right? The y-intercept is 0. This goes around the origin because it's centered at the origin, so I would expect there's going to be 2 solutions. So this one asks us to solve it using substitution. How do you think you might attack it here to use substitution? What do you think you might do? Yep. We've already got this with second equation to solve for y, right? So just take that 2x and put it in for y into the first equation. So we get x squared plus 2x quantity squared equals 25. When you square 2x, what do you get? 4x squared, good. So combining the like terms on the right-hand side, excuse me, that's the left-hand side. Combining the like terms on the left-hand side, we get 5x squared equals 25. Divide both sides by 5, we'll get x squared equals 5. Easy way to solve this equation is take the square root of both sides, but remember, every time you take the square root of both sides of an equation, what do you get? Plus or minus, right? Every single time you get a plus or minus in front of it. So when we do the square root of both sides of the equation here, we'll get x equals plus or minus square root of 5. And again, like we said, we expected two solutions. The fact that we get two x values kind of validates that we're going to get two solutions, right? I get an x equals root 5 and an x equals minus root 5. But again, remember, we're looking for basically points of intersection for ordered pairs x, y that solve both equations. So I need the y's that pair with the x's. Well, we already have y equals 2x. So it's not too hard to figure out the y's that pair with the x's. If my x is negative root 5, what is the y? Using this equation here. If x is negative root 5, what is y? Bless you. Negative 2 root 5. And if x is root 5, 2 root 5. Yep, good. So that would be the two solutions. Bless you. Questions on this one? Not too bad? Work on the next one for a minute. See what you get. Ready to chat about it? What did you do first? Okay, so you solve for the first one for x and plug in for the second one? Good. That's probably what I would do too. This one's probably a little bit easier to solve for x than y because I can just add the y over to the other side. And then put in the y plus 4 for the y. So far, so good? And then just like we did before, we need to simplify this. So let's distribute. We get y squared plus 4y equals 12. We have a quadratic equation again. Our main method for solving quadratic equations is to factor. How does this one factor? Y plus 6 and y minus 2. So what two solutions do you get out for y in this case? Negative 6 and 2. So far, so good? Can we figure out the x's that pair with these? What do you get? If y is negative 6, what do you get for the x? Negative 2, because we got that first equation, right, that we used to solve for x. And if y is equal to 2, what do we get for x? 6. So what are the two ordered pairs that we'll have? Good, and 6, 2, good. So while you were working, I was playing around with getting a graph to see if we could see what that means graphically. So let me go over here. A little bit. So here's your line x minus y equals 4. If you solved it for y, you would have got y equals x minus 4, so you get that line with a slope of 1 and crosses the y-axis at negative 4. But you can see the solutions, right? Here's your negative 2, negative 6 point, and over here is your 6, 2 point. This okay? So the visual representation of what we're looking at might help. That xy equals 12, the shape is called a hyperbola. Not that you necessarily need to remember that, but that's what kind of a shape it is. Questions on that one? We're so quiet today. All right. This next one actually says to use substitution, which we could do. And let's go ahead and do that. It's probably a little bit easier here rather than trying to solve for x or solve for y, but rather solve for x squared or solve for y squared, right? Probably a little bit easier. Which equation do you want to start with to solve for one of them in terms of the other? Doesn't matter, I just need to pick one. Which one do you want to work with, the top one or the bottom one to solve for one of the variables? The top one? Okay. Which one do you want to solve for? You want to solve for x squared or you want to solve for y squared? X squared, okay. If we solve for x squared, we'll subtract over. So we'll get our x squared equals 9 minus y squared. Take that and plug it into the second equation. So we'll have 9 minus y squared minus y squared equals 1. Or said another way, 9 minus 2y squared equals 1. Let's isolate our y squared. I'll add 2y squared to both sides and subtract 1. Divide by 2, you get y squared equals 4. What do you get when you take the square root of both sides in this case? Plus or minus 2. Good. So far so good? We okay with that part? Cool. All right. Now for each of these, we want to plug it back into the original, or not the original, the first equation. So if y is negative 2, plug that in, we get y squared, or excuse me, x squared equals 9 minus the quantity negative 2 squared. When we simplify that, we get x squared equals 5. Negative 2 squared will give us 4. 9 minus 4 is 5. So just like before, when we take the square root of both sides, we'll get a plus or minus 5. Notice now that this one y value corresponds to 2 different x values. That's giving us 2 solutions already, right? Do the same thing for y equals 2. We get basically the same equation and the same solution, x equals plus or minus 5. But again, for this other y value, we get 2 solutions. So how many total solutions are we going to end up with? How many in total do we have? Got 2 when we used y equals negative 2. We got 2 when y equals 2. How many do we have total? 4, yeah. So what are they? Okay, that's one of them. Yep, I agree. And also a 2, yep. For the yep. So the same x values, but also do the y's for negative 2, right? Oops. Close my parenthesis too soon there. So again, we get root 5, negative 2, negative root 5, negative 2, root 5, 2, negative root 5, 2. Oops, I got my negative on that last one, didn't I? So we end up with 4 solutions there. Is okay? Let's see what this would look like graphically, real quick. Go back over to Desmos here. Clear those out. One of the equations was x squared plus y squared equals 9. And the other one was x squared minus y squared equals 1. Oop. Zoomed funky. Oh, almost a little bit more circular. So that x squared plus y squared graph is that circle here. Again, if you have x squared plus y squared equals a number, that always gives you a circle that's centered at the origin, and the radius is the square root of the number on the other side. So you get a circle of radius 3. That x squared minus y squared equals 1 is a hyperbola again, it's just not rotating. And so we see the 4 points of intersection there again. What questions do you have on that one? Is that okay? Now, notice this problem specifically said do it by substitution. But looking at your system of equations here, do you think there would have been an easy way to get rid of one of the variables quickly? Using a different method? Yeah. Yeah, we could use it. We could eliminate the y squareds pretty quickly just by adding the two equations together, couldn't we? Right? So if instead you did elimination, if I added the two equations, what would you get? Two x squared equals 10. And notice you're going to get that x equals plus or minus root 5 thing again, aren't you? And then you could use those values to figure out what the y's are. Does that make sense? So you could have also used elimination. So let's practice a couple of different ones that have elimination, which is what I'm pretty sure the next problem does. So let's look at this. X squared plus y equals 0. And then x cubed minus 2x minus y also equals 0. So the x, just to graphically show you what's going on here, your x squared plus y again, if I solve that for y, you would have y equals negative x squared. So that's the parabola that's flipped upside down. Right? That's the parabola that's upside down. The other one would be a cubic equation, right? Remember your cubic ones either go from lower left to upper right or vice versa. And this one's going from lower left to upper right there. Just trying to remind us of things as we're thinking about final coming up as well. All right. You could do substitution. There's nothing wrong with doing substitution. But notice again, right here, I can easily eliminate the y's by just adding the two equations together, can't we? We agree with that? If I just add the two equations, the y's go away pretty quickly. Okay. So if I take the x squared plus y equals 0 and the x cubed minus 2x minus y equals 0 and add them together, we just end up with x cubed plus x squared minus 2x equals 0. The y's go away. Again, our main method for solving equations that aren't just linear is to factor, right? If it's a quadratic or this one's a cubic equation that has an x cubed in it. Our main method is to factor. What can you factor out first? X, good. That leaves you with x squared plus x minus 2. How does that factor? Good. X plus 2x minus 1. Good. So what three solutions do you see from this equation? Good. Good. Positive 1. Good. Exactly. Yep. 0, negative 2, positive 1. That's exactly right. And even though I cut off the graph when I put it on your handout there, you can see that these two things are getting closer together over here. They're going to cross at some point. And then you see the other two solutions as well. We found the x coordinates. How do we find the y coordinate? Yeah, substitute it into either of the two equations. Which one's probably easier to substitute into? The top one, right? So if x equals 0, we have y equals I'll move the x squared over. Negative 0 squared, which is certainly 0. Put in negative 2, you should get negative 4. And if you put in 1, you should get negative 1. I just used the first equation and moved the x squared over, right? So you get y equals negative x squared. So what are the 3 points that give you solutions then? Questions on that one? Okay. All right. We'll practice more of these on Monday, as well as talk about your test on Wednesday. So, otherwise, have a good weekend. Why don't you go a few minutes early here today?